Okay, so let's take a look at this now. In section 5.2, well, section 5.1, we learned about how to find eigenvectors. In section 5.2, we're going to talk about how we can find eigenvalues. Okay, how are we going to find eigenvalues? Okay, so eigenvalues, of course, are the lambda values to this equation here. So the key to finding eigenvalues is by solving what's called a characteristic equation. What's the variable here in this it's an equation, right? Because you have well, a minus lambda I, okay, a minus lambda I is going to be a matrix. But when we take the determinant of a matrix, we're going to get a scalar. So this is just a regular equation. And the variable is lambda. And we can find eigenvalues by solving this characteristic equation. Let me show you why. So when we want to find eigenvalues, what we're doing, we're saying, well, okay, I want to find all scalars lambda such that this vector equation, okay, that vector equation is the same one that you learned about in section 5.1. Okay, when you try to find the eigenvectors of a matrix A, okay, you are solving a system of equations given by this homogeneous system. But of course, that homogeneous system comes from this vector equation. So we want to find all scalars such that this vector equation has a non-trivial solution X. And we know that's true because the definition of an eigenvalue is such that A times X, so the definition of an eigenvalue lambda is lambda satisfies the vector equation A times X equals lambda times X, where X is not equal to the zero vector. So that boils down then to solving this vector equation here. But we have to get the determinant involved in here, right? That characteristic equation is the determinant of A minus lambda I equals 0. That's how we're going to find the eigenvalues. So we have to get the determinant involved here. So, all right, if you have A minus lambda I times X equals the 0 vector, then X would equal the inverse of A minus lambda I. That's a square matrix. X will equal the inverse of A minus lambda I times the 0 vector. And that equals a 0 vector if and only if A minus lambda I is invertible. Okay. Now the question is, do we want A minus lambda I to be invertible? If we're finding eigenvectors, do we want A minus lambda I to be invertible? Well, the answer is no. And why is the answer no? Who can tell me? If we're finding the eigenvectors of a matrix A, that's right. Excellent, Andres. If we're finding the eigenvectors of a matrix A, okay, then if A minus lambda I is invertible, that would mean then that that would mean that this equation here, I want to say it the right way. This equation here, and we applied it in the example in the section 5.1. That's the equation that we use to determine our eigenvectors. But we don't want the eigenvectors to equal 0. Well, they can't. An eigenvector cannot equal the 0 vector. But if A minus lambda I is invertible, well, when you solve this vector equation, you're going to get that x equals the 0 vector. And so you don't have an eigenvector. So that means to solve for the eigenvectors, A minus lambda I cannot be invertible. Okay? It cannot be invertible. But if A minus lambda I is not invertible, what does that tell you about the determinant of A minus lambda I? That's right, Hung. It equals 0. And that's the key. There's your characteristic equation. Okay? So if we don't want our vector x to equal 0, then A minus lambda I cannot be invertible, and hence the determinant of A minus lambda I is equal to 0. Okay? And that's the characteristic equation that in our discussion, that is called the characteristic equation, and that's how you're going to find your eigenvalues. Okay, are there any questions on that? Okay, excellent, Eleanor. It's always good to know why things are true, I think. If it's, of course, sometimes it can take some of these concepts to prove them, could take, to really understand them, it could take half an hour to go through a proof and really feel comfortable. But, this is fine, what we got here. So, okay, let's go ahead then and let's look at an example. May I move forward here? We're good? Are there any questions? Okay. Well, all right. Here's an example. Here's an example. Okay. And I used a very special font here for the example. It kind of looks like my handwriting. a very special font on the computer. It simulates my handwriting. Isn't that amazing? I don't think anybody believes that, but all right. You know, a lot of examples I do have typed out like formally, but not all of them, but it's fine. It's fine. The key is let's look at examples and learn. So here we want to find the characteristic polynomial and eigenvalues for this matrix A. Now, characteristic polynomial is the characteristic equation without the equals 0. It's the left-hand side of the characteristic equation. And this example, this is actually, this corresponds to a matrix A that you're going to see in section 5.3, the third example. So I thought, let's find the characteristic polynomial of that matrix. And then find the eigenvalues. Okay, so characteristic polynomial is this, the determinant of A minus lambda I. So you're computing a determinant, and you have to use the rules you've learned for computing a determinant. Do you think the rules, well, I want to be careful. Do you think the three rule, well, I want to say, so you learn how to compute a determinant using cofactor expansion, and also you learn how to compute a determinant by, this is back in chapter 3, using properties of determinants. Do you think properties of determinants are going to be easy to use here? It's going to be hard to apply the properties of determinants to compute this determinant here. And why is that? We're going to have to use cofactor expansion directly. Why is that? Why would using properties of determinants might be hard for computing this determinant? What would make it a little bit hard? What's sort of different about finding this determinant as opposed to all the determinants you found in the past of matrices? What makes this determinant here more interesting? What do you have in this determinant that you don't have, that you've not had in other determinants before? I'll give you a hint. You have a hold on. In this determinant, you have a well, man, nobody can get it yet? The word I'm looking for? A variable. That's right. Good, funny. Good, Catherine. You have a variable in this determinant. So applying the properties of determinants could get messy. So we're going to do cofactor expansion directly. Now it's going to be interesting because this is a dense matrix. There's no zeros in this matrix. Now in your homework, the matrices you have, when you can find a characteristic polynomial, you will have some zeros in those matrices, and that'll make life a little easier for you. But let's just go ahead and work this out. So, okay. I always think of this little helpful matrix here because, you know, for determinants, you have to worry about the plus or minuses in front of the numbers. But so A minus lambda I would be equal to this matrix here. The matrix A is, of course, 1. Well, along the diagonals, you have 1, -5, and along, sorry, for the matrix A, you have along the diagonal 1, -5, and 1. And so the identity, you know, the identity, if you have, you know, lambda times I, okay, that would just equal, okay, let me see here, let me use my stencil. So this is an aside here. Lambda times I would just equal lambda 0, 0, 0, lambda 0, and 0, 0, lambda. Right? So let me just kind of separate this. Okay. Okay. So think now of taking the matrix A and subtracting lambda minus I, and it's only the diagonal entries that get altered. The other entries, since the other entries off the diagonal, you're subtracting, you know, zeros, the other entries stay the same, these other entries. And so what I'm going to do is I'm going to use cofactor expansion, and I'm going to do cofactor expansion along the first row. Okay, just because the first row for me it's a little easier, the first row. You've done cofactor expansion before, so this shouldn't be a problem. Okay, and of course, you have to get the determinants of all of these 2x2s, right? You have to get the determinants of all of the 2x2s, 2x2 determinants. And so if you do that, then you're going to get what you see, what I show here. Okay, and this here, I'll give you a moment to copy it down. This is -3 lambda plus 6 at the bottom here. Please let me know if you have any questions. What I did was I computed each cofactor, and then the cofactors I simplified what's in the parentheses as well. Okay, so give you a moment to copy that down. Please let me know if you have any questions, okay? Please let me know. And while we're, well, yeah. Okay, so we're going to have 1 minus lambda times lambda squared plus 4 lambda plus 4 minus 3 times 3 lambda plus 6, and then plus 3 times 3 lambda plus 6. May I move to the next page? Maybe give me a thumbs up when you're ready to go to the next page. Okay. All right, let's go to the next page. Thank you. All right, and so the characteristic polynomial, well, something nice happens. You get two terms that cancel out. And so you're going to get and lambda squared plus 4 lambda plus 4 factors as lambda plus 2 times lambda plus 2. Now the way my math lab homework is going to want your answer. I wrote the final answer in factored form right here. But my math lab, I believe, is going to want you to write out your characteristic polynomial, like expand it out in unfactored form. So they would want you to multiply everything out. Okay, just to let you know that. Factored form's better, because factored form, then you can identify your eigenvalues. Because what are you going to do? You're going to take your characteristic polynomial and set it equal to 0, right? That then's your characteristic equation. And so if you set determinant of a minus lambda I equal to 0, then 0 equals negative lambda minus 1 times lambda plus 2 squared. That means the roots of this equation, the solutions of that equation, are going to have to be lambda 1 equals 1 and lambda 1 equals negative 2. And also you have corresponding multiplicities. So the factor lambda minus 1 only occurs once. So the eigenvalue lambda equals 1 has multiplicity 1. The factor lambda plus 2, well, that occurs twice because it's lambda plus 2 squared. So that factor is going to have that eigenvalue is going to have multiplicity 2. What they'll do, though, in the homework, they realize, I mean, normally, like for these, this is a third order polynomial. And you can't use quadratic formula on a third order polynomial. So in order to work it out, to find the roots, you have to use like graph the polynomial on your calculator. To find the eigenvalues, you have to graph the polynomial on the calculator and find the roots. But I don't think any of the problems, like where you have to get the characteristic polynomial, involve you doing that. Because we can do that very easily. I mean, we can find programs that'll find roots, of polynomials. We don't need to get into the rational root theorem or anything like that. But are there any questions on this? Okay, who's reasonably comfortable with this? Who's feeling good? with section 5.2 so far. Okay, name is good, that's good. And are there any questions? I want to make a comment before you go, but are there any questions? All right, thank you, Ariana. You're comfortable? Good, good. Good, excellent. All right, let me stop the recording.